So we've all seen stuff boil. If you spend any time in the kitchen, chances are you've cooked stuff in boiling water. So you've heated the water. Eventually gas bubbles started to form and eventually the whole thing was boiling. But what exactly is this notion of boiling point? Well, the temperature of any substance is a measure of its average, is proportional to its average kinetic energy. So temperature is proportional to, this means is proportional to, so temperature is proportional to average kinetic energy. So when we increase the temperature of any substance, then we know the average kinetic energy is going to go up. So when the kinetic energy of a typical or average molecule goes up, chances are there are more molecules in that substance at that particular temperature than at lower temperatures that are now able to escape from the liquid phase into the vapor phase. And every molecule that escapes from the liquid phase and becomes a gas, it exerts a pressure on the atmosphere around it. So this exerts pressure, and this pressure is exerted in all directions. This exerts pressure, and so on. And it makes sense, the more molecules of gas we have, the more the pressure exerted by this vapor. Now, boiling point, the boiling point of any substance is the point at which the vapor pressure, so that's the pressure exerted by the gas molecules, the molecules that were liquid molecules and had enough kinetic energy to escape into the vapor phase, they exert a pressure. So it's that at the point at which the vapor pressure equals the atmospheric pressure, that point is termed the boiling point of any liquid. So on the surface of the earth, where we all spend time in the kitchen, the atmospheric pressure is 1 atmosphere. So when we boil something, we boil something on the surface, right? The atmosphere near the surface is exerting a pressure, 1 atmosphere. And the pressure at any point, the height dependent pressure, is dependent upon the weight of the column of air, the atmospheric column of air above it. So it should make sense at higher altitudes you have less air above. So this is the surface of the earth, right? Say this is the surface. This is, say, 10,000 feet. At this point, there's less air above than there is at this point. So here, it makes sense that at 10,000 feet, the atmospheric pressure is lower. So when you're on the surface of the earth, the ambient pressure is 1 atmosphere. And when the temperature of a liquid gets high enough so that enough molecules escape into the vapor phase, and these molecules, enough of them escape into the vapor phase to exert a pressure equivalent to 1 atmosphere, then you reach the boiling point of that liquid. And for water, it's 100 degrees Fahrenheit. That's about 100 degrees centigrade, and that's 212 Fahrenheit. At 1 atmosphere, when the ambient pressure is 1 atmosphere. However, let's say before the advent of pressurized cabins, if you boil water and you were in a plane at 10,000 feet. So let's say you're in an airplane here. This is a crude drawing of an airplane, and you have this pot you're trying to boil. So let's say, for argument's sake, I don't know if this is actually the case, but let's say the ambient pressure is 0.7 atmospheres. Well, now you need less vapor. Remember, the vapor pressure is proportional to the amount of molecules of gas that you have. So you'll need less molecules of gas to exert 0.7 atmospheres of pressure than you would 1 atmosphere. So it should make sense that at higher altitudes, or at lower, when the ambient pressure is lower, the boiling point is lower as well. So the temperature required for boiling is lower. So we'll say at lower ambient pressures, the boiling point of any substance is also lower. And of course, at higher altitudes, here I'll just say higher altitudes, lower atmospheric pressure, and this means lower boiling point. This is not blood pressure, this is boiling point, at least in this case. So hopefully that gives you some intuition into what the boiling point is and why it varies as a function of atmospheric pressure.